Tuesday before I get this posted, so that should get us going there. Just a couple of quick announcements. The pricing is going to go up by $25 for the Berlin trip on September 1st. And what my understanding is, what you've got to get in to lock in your price is just the deposit. So if you want to get in, and the price increase isn't huge, it's a $25 price increase. So if you're working on it, and that's the part I know for sure that's not refundable. Other monies are refundable, but the $95 deposit is not. But if you're considering it, also if you're interested, and I know I've got about 3 of you that are kind of in that I'm really, really interested, go ahead and click the I'm interested one so that you get updates from EF about how to pay for it, all of that kind of stuff. So that part really does help, because you'll get different information if you're just interested and haven't even paid the deposit. So I know there's a couple of you that are in that category of things. So I suggest you go ahead and do that, even if you don't do a deposit. Just click on that part, and that way you get the most up-to-date information as we go through. All right, so where we've been is you guys have done simple harmonic motion. I should have simple harmonic motion files uploaded into Blackboard or something along those lines. And then we are working on the Doppler effect one as well. So, and we'll start talking about the Doppler effect today, perhaps. So I'm gonna focus more on the concept stuff today, but we're gonna get really going on dealing with the traveling waves. So I'm gonna go to the document camera first. We'll see how this works. This is lovely, lovely part. One thing that we're not there. We're there on there, but there we go. Yeah, the document camera is doing weird stuff. I have record press, so we're good there. So one thing we didn't talk about on simple harmonic motion, even though we've seen it and we kind of just mentioned, I didn't do anything with a wave equation on it. If I have a spring and it's going up and down, and I'm looking at the amplitude over time, we know that we end up getting something that actually looks a little bit more like this. And eventually it stops. And usually what happens is there'll be a curve. I can actually draw a curve through these max-mins. And that's referred to as dampening. And dampening occurs due to a loss of energy, and it's a loss of energy due to those non-conservative forces. So things like friction, which is going to be, most of the time in this case, is going to be air resistance. In metals, we sometimes will get heat. And we can actually increase this. We can actually make the dampening go much, much faster. Depending on our situation. This is why we want to have shock absorbers. That's one where we want it to dampen very quickly, so that we don't get bounced around and have things that are really jolting us. So we end up with dampening. And so it's an interesting concept, but it's due to that fact that we're losing energy due to the friction, air resistance, heat. Sometimes we're actually kind of making sure that if I have a fluid, that I'm actually pulling that away in order to get the bouncing to stop. And if anybody's ever seen a Foucault pendulum, has anybody ever seen a Foucault pendulum? At a big museum somewhere? Usually these are the pendulums that it's going around in a circle, and they'll have like dominoes or little blocks. And this is actually how you can prove that the Earth rotates. And the pendulum, what? Oh, there you go. And each time the pendulum swings, it moves a little bit and it'll knock over the blocks. So as through the course of the whole day, it'll make it traverse the whole circle. And they're usually very, very long. Usually you'll see them in, at UCO. If you ever go to UCO, there's one in the science building. And it's a 3-story pendulum. And the radius or the diameter of this circle is only about 3 feet. But what they do is they put a little electromagnet in the middle, and your pendulum ball is magnetic, so it gives it like a bump in order to keep it going. So we don't lose it for dampening, to be able to demonstrate that the Earth actually rotates. All right, so what we've done so far is we've talked about oscillators. And we've talked about simple harmonic motion. And we use that lovely sine wave, right? That lovely sine distribution, or cosine, as the case may be. That my wave was described as my y was going to be my amplitude cosine omega t plus some phase angle. And basically we're going up and down. But we know that when we encounter waves, they aren't just going up and down. So now we're actually going to start talking about wave motion. And we're going to start that idea with a string. So if I take a string, I can actually put a pulse into it. And we can know that this pulse is actually going to progress down my string. You know, we've done it, we do a jerk up and down, and this pulse actually goes down on the string. And if I'm looking at the motion of this pulse, if I'm sitting here at this spot on my string, I've got my little spot, as the pulse moves through, this spot is going to go up and down. It's not changing anywhere on my string, but it will move vertically up and down as this pulse goes down the string. So this little point is going to act as an oscillator. And a little further down on my string, I've got another oscillator that's going up and down. So I can look at my string. You know, I can look at this string as a series of connected oscillators. So if I'm in a rope or a string, I can do that. I can make that way that it looks. And I can describe, and if I'm looking at this, that's describing the motion of this going up and down, but I have this pulse that's going along in the x direction. So it's actually moving along my string, and I have a pulse. So I can actually write a wave expression. So I can write a wave expression that's going to be my maximum height, which is going to look like my amplitude, right? That's going to look like the amplitude, or the height of my pulse. And it's going to be, and I'm going to use a sine function this time. And I've got a kx omega t. And the k is kind of like my spring constant. It's going to be dependent upon what my string is made of. It's going to be dependent upon the tension in the string. It's going to be dependent upon a number of different things, and that's where my k is going to come in. I've got my frequency because it's going to act just like this oscillator, and I'm going to have an amplitude. So when we talk about waves, we got to get some terminology going. So we looked at this before, and this is if it's versus time, right? If this is versus time, this is going to be one cycle. And the time that it takes for this to happen is a period. And we know the frequency is equal to 1 over the period. But we can also look at this wave a little differently. Okay, we can also look at that wave a little differently. And this being related to position. Okay, that being related to position. And in this case, that position, this is going to be something that we're going to do as lambda, and this is wavelength. And in both cases, this is my amplitude. So the amplitude is going to be the deflection from the position. So I'm going to show you a GIF that really kind of hits home this idea of being in a series of oscillators. And I want to go to, there it is. So if we look at this as the top of a wave, top of a water wave, say, think of it as a water wave coming through, watch what's happening to the red ball. It's still part of that same column of dots. It's not changing its column of dots, but you can see how it's going around the circle. So we already said simple harmonic motion looks like a circle. And this is kind of graphically showing you that the motion as the wave travels through a spot on that medium, it's going to look like it's traveling through the circle, and my ball is going up and down, just like a series of oscillators. So we can look at a traveling wave as just a connected bunch of oscillators. So we can really, really look at it from that perspective, and that's really helpful to us. So now we can look at waves and some other aspects of them. So when we deal with waves, now what we're going to deal with right now, maybe, oh, I'm hitting the wrong button. There we go. Hitting the right button now. If I'm dealing with a stream, if I'm dealing with water, if I'm dealing with a variety of things, we're talking in this case about a mechanical wave. Now, mechanical waves are going to behave in a certain way. The first key thing about a mechanical wave is it has to have a medium. A mechanical wave is always traveling through something. It's going to be a string. It can be a fluid. So like in my water, and we've seen a wave travel through water. It can be material, like a block. It can be a metal. Or it can be a gas. So mechanical waves require some sort of medium. And that medium is going to have certain properties. If I'm dealing with a string, it'll have something that looks like that. And this is usually referred to as linear density. Water, metal. Now, if I have a block of metal, I might use a Young's modulus. But gases and waters, I'm going to use rho, which is just a bulk density. So I'm going to have bulk densities, I'm going to have linear densities, I might end up needing my Young's modulus depending on what I've got. And in fact, when we actually deal with it, you'll find that the rope and my metal and my gas and my water are all going to impact how a wave travels. And if you think about it, we know this intuitively, right? If I've ever been swimming and I'm under the water, we know that sound is going to travel under the water differently than sound travels in air, which is going to be different than sound travels through a piece of metal, which will be different than how sound travels through the ground. Because we've all watched the cool nature shows and then they know that there's a void underneath, because they've gone in and they've done a shock and then they've read the reflection patterns of that shock wave in order to tell if there's something that is in there. Anybody watch Oak Island? The Mysteries of Oak Island? Anybody watch any of the archaeology shows where they're actually taking little radars and going into the ground? Because that's what we're going to actually be looking at, and that changes in density changes how the sound is going to move or how the wave is going to travel. And we've all had Chem 1, right? We've all had Chem 1, and in Chem 1 we learned something. One of the things that we learned was the velocity of the wave is related to the wavelength times the frequency. Because we always knew that the speed of sound, or the speed of light, sorry, the speed of light is equal to the frequency times lambda. And if I'm in chemistry class, sometimes that would look like that nu times lambda, and that gave me my speed of the wave. Now, this speed of the wave is for electromagnetic waves. And we're going to see this down the road. One of the big differences between these two waves, the mechanical wave and the electromagnetic wave, is my electromagnetic wave does not require a medium. Mechanical waves require a medium. Electromagnetic waves, my tongue is tight. Electromagnetic waves don't require it. They can travel through a vacuum. These do not. They have to have a medium. So let's look at that for a second, and let's just actually talk about it just a hair. So if we go back and we start with our wave function, and we're actually going to call this a wave function. Let's look at the math associated with it. Okay, and we'll call this a wave function. Interesting things about this. First of all, we know that this is going to go from minus y max to y max. So the range is going to go from y max to minus y max. And then it'll have all the values in between. But it'll be at y max when sine kx minus omega t is equal to 1. And it'll be at minus y max when sine kx minus omega t is equal to minus 1. And one of the things that we know, if we just look at this one right here, for sine to equal 1, kx minus omega t, at a minimum, has to be a multiple of pi over 2. And if we look at this function, and if I'm doing a positive 1, right? I'm doing a positive 1. That's pi over 2, or it's 5 pi over 2, or it's 9 pi over 2. It can be minus 1 at 3 pi over 2 and at 7 pi over 2. But when this right here, it has unique solutions. So it has unique solutions to allow for it to be there. And we're just gonna use the easy solution to start with. The k minus omega t is equal to pi over 2. But this is one of those solutions. So remember when we're in chemistry class and we talk about quantum numbers. Hang on, I'll get there. When we talk about quantum numbers, these were unique solutions to the Schrodinger wave equation. So here, I'm going to get unique solutions to this mechanical wave equation that this will allow me to be at y max or minus y max at a specific value. Same thing happens with quantum numbers. It allows me to have specific values for the solution to the problem. And they're unique, uniform solutions. So if I did this, right, if I just said, and from the math part, if I just said that the absolute value of k minus omega t is equal to 1, or not, I'm sorry, let's do it this way. That the sine of kx minus omega t, we want the absolute value of that equal to 1, where I'm not caring whether it's positive or negative. I want that absolute value of it was going to equal 1. Then kx minus omega t is going to be pi over 2, 3 pi over 2. It'll be 5 pi over 2. 9 pi over 2. We could actually write that as 1 plus 2n, where n is equal to 0, 1, 2, 3, right? And so that could be kx minus omega t is equal to 1 plus 2n pi over 2. Now you can see where the quantum or the quantizing comes into play. And when we get to quantum mechanics, either in chemistry or quantum mechanics in physics, now you can start to see that we have unique solutions that are based off of integers. And so we can actually see that part to it. So we're going to go back, and that's just kind of that's what the mathematics start to give us, and it starts to tell us quite a bit. But we're going to go back and we're going to use our kx minus omega t is equal to pi over 2. And we're going to solve for x. So x will ultimately be pi 2k plus omega over k t. And for those of you who've done differentiation, and even those of you who haven't, we've started to see it. So if I do dx with respect to time, that's a constant, so it goes away. I get omega k. But we know what that is. That's velocity. And this is the velocity in the x direction. So the velocity in the x direction is either going to be omega over k, or we can go back and do the velocity in the x direction is going to be lambda over the period, or it's going to be lambda times the frequency. The difference between my mechanical wave and my speed of light wave is this is not a constant. But it will turn out that speed of sound is a constant, but it's also going to be the frequency times the wavelength. And it's going to be the speed of sound in metal, or the speed of sound in something else, but my speed is going to be a little different. Going back to this idea that my material makes a difference, and your book does a really good job, and we're not going to beat on it too much, that the speed ends up being the tension in the string divided by its linear density. And your book gives you a really nice example of where this comes up. and they actually write it out like that. I do encourage you to do that, but for the sake of time and all the stuff that we have to cover, I'm not going to focus too much on it. Which also means that you may have a couple of homework problems associated with it, but you're not likely to see it on a test. I expose it to you, but you're not likely to see it on a test. And part of it is it's so material dependent. Where this will come into play that we have to be important with is when we get something that's called a standing wave. And that won't be until the next chapter, but I want to kind of bring it in. And we've all seen these pictures, right? So I have a guitar string, and if I have a camera or something else, I know that I can create a wave that's going to look like this. And we call that a standing wave, where these are called antinodes, and these are called nodes. And these are fixed solutions. So we get back to that idea of a wave equation, because these are fixed solutions. Because I can have a system where I have my endpoints, and I can have a half a wavelength. That's a half a wavelength. Or I can have a system where I end up with just one complete wavelength. I'm not drawing it very well. But in order to get a standing wave, the boundary conditions have to be just right. If I don't have it where these nodes end up on the closed end of my vibration, it's not going to work. I'm just going to get a mess. And it's going to look funky. And it's going to be ugly. I'm going to get a mess. So we end that. So what ultimately happens where I'm dealing with this tension versus my linear density, you can look at it again from a series of oscillations, a series of oscillators, that the velocity of the wave through the medium, whatever it might be, a string, a piece of metal, it's going to be something called the restoring ability. Can't spell today. Divided by an inertial quantity. If it's something like air, it can be the bulk modulus divided by the density. So let's go back and let's look at our wave in a string and talk about a little bit different from that perspective. So if I have a wave in a string and I send down a pulse, I'm going to send my pulse down, and we know that it's actually moving. The fact that I get a deflection from the horizontal along that string is something that we're going to call a transverse wave. It's actually going to deviate from my horizontal piece. Water, when we have a water traveling wave in the top of water, that is going to be a transverse wave. So I'm going to get transverse waves where I actually see a clear deviation from a fixed point. Now, usually I have slinky at this point because there's another type of wave. So I'm going to switch over. Let's see if I got it. I'm going to switch over. I have a whole bunch of physics gifts here. This is the one I want to look at. So this is a speaker. So looking at how the speaker, you can see that the speaker's got a diaphragm. It's moving up and down. And it's actually going to be, even if I didn't hear a sound with it, what I am seeing is it's doing something physically. It's pushing on the air. It's acting like a plunger. It's going back. It's acting like a piston. It's going back and forth. And that's what's actually going to cause us to have sound. So now if I go back to the document camera, maybe. Okay, got that part. There we go. So now I've got my little speaker. And this is done by a magnet, by the way, because you can actually create a speaker. The speaker is going back and forth, and if I'm looking at what's happening, and I've got my little air molecules, it actually is going to compress and make things denser. And then as it pulls back, it's going to not make things quite so dense. And then it's going to come up again, and these are sending it traveling down the way. And if I'm thinking of it as a slinky, we know how it travels in a slinky. And then I got really tight curls. I'm not doing that very well. I got really tight curls, and then I got really loose curls. And then I get really tight curls again. And then I get really loose ones again. I get this change in density, and it's called, this is called rarefication. And this you might consider compression. What's happening here with my slinky, I'm going to get, these are going to be compressed, and these are going to be stretched. So I get compression and stretching. Because of what's happening, if I think of it on an atomic scale, I'm going to squeeze those little atoms together, and then they're going to extend out. I'm going to squeeze them together, then they're going to extend out. I'm going to squeeze them together, and then they're going to extend out. It's kind of like an accordion. Okay? Kind of like an accordion, kind of like that piston. This type of a wave is called a longitudinal wave. So I have transverse waves, or I have longitudinal waves. Sound is going to be a longitudinal wave. Water, strings, those kinds of things are going to be transverse waves. So I'm going to get compaction, rarefication, as it goes. Now, I can still use the same wave function, how tightly they're compressed, or how lightly they're compressed, and now I can actually use the same wave function to describe that motion. So the motion, whether I have a transverse wave or I have a longitudinal wave, I can still describe it graphically the exact same way. I can still use that same mathematical function to do that. But the idea now, though, is if I'm actually compressing my waves, right, that means I'm getting a change in density, and that can lead to two critical things. One, for this to happen, I have a transfer of energy. And that's kind of easy to see, especially if I'm in a metal, right? If I'm sending a pulse of a wave and I'm doing compression, this thing is going to bump into something along the way, and I've got a series of collisions. So I can take that Newton's cradle thing and just continue it on from this point of view. So I'm getting that compaction, rarefication, compaction, rarefication. I've got a series of collisions going back, and so it's kind of easy to see that I'm getting that transfer of energy. The other thing that's happened is I've got a force per unit area. So I can also have a pressure. Okay, I'm about to tell you that this chapter is going to get really confusing, because we're starting to talk about sound related to pressure, which is force per unit area, and the intensity of sound, which is power. We're going to use two different P's in the same chapter and one is related to power, and one is related to pressure. So you got to kind of keep track of what's going on. So from a conceptual idea, let's look at a shock wave, because you can easily see that A, it's going to have power, B, it's going to have pressure, and C, that this sucker is moving, even in a medium that we can't necessarily see. So I'm going to do this, and this is what we're going to probably end on today. So we're going to do this BBC one. Big screen here.
Today we're going faster than the speed of sound. And what better way to get there than by blowing stuff up?
So most people might be familiar with the Doppler effect, even if they don't know it. What sound does a Formula 1 car make, Si? Exactly, so the car's going so fast, as it's travelling towards you, the sound waves its engine's producing are actually getting compressed in front of it because it's catching up with those sound waves. And then as it's going away, the opposite's true, so that.
So it's kind of like when the object itself is travelling faster than the actual sound waves being emitted, then you break the sound barrier.
That's when you break the sound barrier, exactly.
Right.
You get this so-called sonic boom, and jets produce this sonic boom. And booms don't come much bigger than an explosion. And I'd love to see if the explosive boom is breaking the sound barrier, if we can measure that. So we're joined today by John from Orpha Technologies, and so this is it.
This is about 250 grams, 8 ounces actually, of PE4. That's a British military high explosive, as it's standard high explosive for miscellaneous demolition tasks.
Great, and that should give us a big enough bang to see this shockwave coming.
Certainly it should, and we've got very good conditions for it today because the air is quite damp, and that tends to give you a better chance of seeing it.
This apparently can take the glass of an RPG, so I think we'll be alright.
Yeah, yeah.
3, 2, 1.
Whoa! There we go, we got it! Hey.
And you can see that's just in front of the explosion, so that's the explosion really driving that high pressure air outwards. It's sort of condensing the air down so much that it's bending the light coming through.
Wow.
So the light's sort of going at different speed as it comes through. That is amazing.
I'm pretty happy we got that.
Well, what I'd love to do now is try and sort of get some markers down and actually measure how fast that's going. So to work out the velocity of the shockwave, we obviously need some distance markers. So we've got our old favourite, water balloons, and I'm just going to measure this one out to about a metre away from where the explosive is going to be, and then slightly offset them so that the shockwave doesn't sort of get blocked by this one in front, if you see what I mean.
5.
Whoa! Oh, you see the shockwave there though, that looks awesome.
And actually that's the beginning of the shockwave, you can see just as it hits it. Cool, so that's about 5 frames between the balloons and that shockwave movement there. So speed equals distance over time, so in 5 frames the shockwave covered about 50 centimetres. 5 frames of 6,250 per second equates to 0.0008 seconds. So at this point it's moving at 625 metres per second, which is much faster than the speed of sound. Awesome.
Well, I've had an absolute blast today.
Hey. Me too. But remember to subscribe because we're going to be back here in the quarry for more explosive action in the future and you don't want to miss it. Today on Slow Mo, we're going to be filming one of the most destructive forces on the...
So get you looking at the speed of sound, and then we'll talk a little bit more about the speed of sound on Monday, start looking at some things and looking at shock waves and Doppler effect. But this gives you that you can actually see that transfer of energy and that intensity that goes through, and we'll have fun on, what is it, Wednesday that we meet again? Because we don't have class on Monday because of the holiday, and so we'll meet on Wednesday. So you guys have a good weekend.